A 6 ohm flashlight bulb is powered by a 3-volt battery with an internal resistance of 1 ohm. What are the power dissipation of the bulb and the terminal voltage of the battery? We can go ahead and draw the battery, the EMF of the battery, which we'll write EMF, and that is 3 volts. The internal resistance of the battery, you can put it wherever you want in a circuit like this, but I'll indicate it here. This little r, I'll represent that as the internal resistance of the battery. And then it's connected to a flashlight bulb, which I'll just represent as another resistor, R, which is 6 ohms. And just to be clear, the battery, I'll draw it in purple here. From the outside, you don't really see what's going on, but basically there's a power source, an EMF on the inside, and some internal resistance. So once we see a diagram, a circuit diagram that has more than one resistor, it's often worthwhile to think about representing this as a single resistor, equivalent resistor. So this is the equivalent circuit diagram where the equivalent resistance, because these resistors are in series, is just capital R plus little r. In other words, we have a circuit that has an equivalent resistance of 7 ohms and an EMF of 7 volts. So in any case, what we want to do is relate these quantities to figure out what is the power dissipation in the bulb. It'll be a lot easier to know that once we know how much current is flowing in the circuit. And so we might as well start there. Let's determine how much current is flowing in the circuit. Apparently, the voltage across this equivalent resistor is equal to the EMF of the battery, and by Ohm's law, we can relate this to the current and the resistance like this. So to solve for the current, let's rearrange EMF divided by equivalent resistance. We have an EMF of 3 volts. The equivalent resistance is 7 ohms. So what we've learned is that the current flowing through is 0.43 approximately amps. That's not our final result, but this is a useful number that we can now use to figure out other quantities. In particular, if we want to know what is the power dissipation in the bulb, the power consumed by the bulb, you can always start with the amount of current flowing through times the potential difference across. Now, if we knew the potential difference across the bulb, that would be great, but why don't we just jump to another relationship that tells us what the voltage across the bulb is in terms of the current going through it and its resistance. Why compute it separately if we don't have to? In other words, the power consumed by the bulb can be written as I times R. In other words, I squared R. And now if we want, we can plug in the current that we found, the resistance of just the bulb, because that's all we're interested in is the power consumed by the bulb. The resistance is 6 ohms, and we'll compute that to be about 1.1 watts. That's the power dissipation of the bulb. Finally, what is the terminal voltage of the battery? By that, we want to know what is the difference in the potential between the positive and the negative terminal of the battery. We want to know what is delta V. Well, to compute delta V of the battery, delta V battery, remember that what it depends on is not only the EMF, but the little bit of potential voltage loss because of the internal resistance. So this is minus I, the current flowing through, times the internal resistance of the battery. We have the EMF of 3 volts. We have to subtract off the current of 0.43 amps times the internal resistance of the battery, which is 1 ohm. 3 minus 0.43 gives you approximately 2.6 volts, which would be the terminal voltage of the battery.